Okay, so this is the second makeup lecture. Last time we stopped with the statement that the Borel sigma field is of continuum power. In other words, if V of R is the collection of all sets in the minimum it's actually the minimum sigma field containing all the intervals, then we said that its cardinality is the same as cardinality of real numbers, which we denote by C. So let me say C, so cardinality of all real numbers, which at first moment we said it might be surprising because it looks like if you start with intervals and take all unions, countable unions, countable intersections, complements and all that stuff, one might think that you describe almost all, if not all, subsets of a real line, but actually that's not true. And the power set of real line definitely has a strictly larger cardinality of R. So power set or particle set of R is strictly greater than cardinality. That is strictly greater than cardinality of R. That's one of the exercises or one of the homework problems that we had in the previous homework. So because of that, if you expect that B of R is almost P of R, one might expect that they are of the same cardinality, these two guys, but in fact this is truth statement, and we're not going to show it because it requires some finite induction on ordinals, and that's something beyond the scope of this course, which is something from set theory and logic. So we are just to take this as granted, but we can see that since B of R is countably generated, we discussed that last time, then maybe it's not so surprising that the cardinality of the cardinality of sigma field B of R, Borel sigma field, is C. And the same thing is true even if you have B of R to D. Okay, well, for any dimension D. So the question is this enough? Is sigma field, Borel sigma field, enough for us to discuss various probabilities? Well, the answer is, for practical reasons in statistics, it's pretty much all you need, but there is some issue that Borel sigma field, some issue with Borel sigma field, because of which we would like to extend this measure to a larger measure called Lebesgue measure. To motivate why we would do that, let's take some examples that are in Borel sigma field. Well, we defined measure as a generalization on real line as a generalization of length. Okay, so we know what the length of one interval is. We know we generalize the length of the joint union of two intervals, or finitely many intervals, or countably many intervals. But then we take a minimum sigma field containing all intervals, and you can extend the definition of length to the sigma additive length function, which we call measure, and you can extend it to the Borel sigma field. That's what we had last time. So let's see what if you have one point. So if A is in R, what is the measure of singleton? So this is not the number A, this is the set whose the only element is A. So one element set. One element sets are called singletons. So what's the measure of a singleton? Well, singleton is in B of R. If you remember, we took elementary sets to be finite union of intervals, and we can we can allow intervals of this kind, okay? And we define the length of intervals as the distance or difference of right endpoint minus left endpoint, which in this case is 0. So measure of singleton is 0. Now when you take finitely many of them, that's again elementary set, and by definition of length of elementary set, the measure of such set is going to be the union, the sum of the lengths of each subinterval, but since each subinterval is actually a singleton, so measure 0, so we have that for any finite set A, the measure, so this generalized length of the finite set is 0, which is kind of reasonable. That's something that you might expect of generalization of length of the interval. Now, what about countably many points? If set A is countable, so let's say A1, A2, blah, blah, blah. What's its measure? So now we have infinitely many contributions, but since each contribution is 0, one may expect that the measure of A is 0, and that is true. And to be more formal, to formally show that that's true, well, you can take A_n to be, so we have a list, since A is countable, we can make a list of all elements of A. So let's take A_n to be the collection of all points A1 up to A_n, okay? And now A_n, mu of A_n is finite, but by what we've just said, because A_n is finite, so its measure is 0. And A_n is increasing sequence, so increasing in the sense of inclusion, and goes to A. In other words, the union of all A_n's is 0, and by continuity from below, which we had last time, we have that mu of A is mu of the union of A_n's and goes from 1 to infinity, which is the limit of mu of A_n as n goes to infinity, but mu of A_n's are all 0, so this is identically equal to 0. This is a 0 sequence, so the limit of the 0 sequence is 0, of course. Okay? That's one way to see, using continuity from below. One way to see that Borel measure of countable set on the real line, and similarly it's when you have R to the D, countable set in R to the D, that it's a measure 0. Here is another way to see this. The reason why I want to show the other way is it might reveal the path that we can go in our attempt to extend definition of length from Borel sigma field to some larger sigma field. And here is the thing. Each AN, each point AN belongs to interval. So here is the thing. So each point, say this is a real line, and we now have countably many points. Now they might be separated from each other with some distance, or that set AN, or that set A might be dense, like Q, which is everywhere dense in R, set of all rational numbers. But for every point, we can take a little interval. Now we know what the definition of the length of each interval is. So take a little interval around each point. So maybe those intervals, if points are close to each other, maybe those intervals overlap. So, but that's not an issue. So take a little interval around each point, And now you can say any point is, since it's contained in the entire interval, some interval, then A is union, A is contained in the union, in the union of all those intervals in. So in is the interval that covers point an, all right? And because of that, and because of sigma subadditivity of a measure, we have that mu of A must be less than or equal to the series of mu of in's. Okay. Now, since this is a series of non-zero of non-negative numbers, we can make each in. We can play smart and make it small enough so that all these terms, when you add them up and take actually a series, all these terms add up to some number sufficiently small. So how can you do that? Well, take any epsilon greater than 0, and for each point an, so for each n, an belongs to, now we're going to cover point an by interval which I will denote by in epsilon, and it's going to be the interval centered at an, but of sufficiently small size, sufficiently small length. So let's say an minus epsilon over something. So let's say 2 to the n. I mean, it's not just, let's say, I have a reason why I'm doing this. At this moment, I will just write 2 to the n in the denominator, but we'll see if we need to adjust that. So the point is that the length of, so measure of in epsilon is what? Is in this case is 2 times 2 over 2 to the n. All right. Obviously, I will have to adjust this, but for the moment, let's take this. And now I definitely have that for each epsilon, I take for each an, I take this interval in epsilon, and for each epsilon, this a is covered by the union of all those intervals in epsilon, because each in epsilon contains its midpoint, which is an. Okay, so that's why we have that, and that's why we again have this. Now, the reason why I chose this particular length of in epsilon is because I want this sum, this infinite sum or this series to make infinitely small. Well, this is series. Now I want this measure to be epsilon over something, so that this adds up to epsilon. But actually, if I take 2 to the n, the geometric series 1 over 2 to the n, when n goes from 1 to infinity, adds up to is equal to 1. So this is really true. But we just need to adjust this length, because the length of in epsilon, we want to be this, but the way we chose gives us 2 over 2 to the n. So just slightly modify, make epsilon over 2 to the n plus 1. So the radius of this interval is epsilon over 2 to the n plus 1. And so then the measure of this guy is going to be just, it's going to be epsilon over 2 to the n. Okay. Well, previously we had 2 epsilon. I wrote just 2 over 2 to the n, but we had 2 epsilon over 2 to the n. But now actually we have epsilon over 2 to the n. So basically we just show that mu of A must be less than or equal to epsilon. For any epsilon, we chose epsilon arbitrary positive number. So for any epsilon, mu of A is less than or equal to epsilon. So that means that mu of A itself has to be 0. Why? Well, if it's strictly positive, we can take epsilon less than mu of A and still have this, so we will produce contradiction. So we see that countable set, this is another perspective why countable set is small in the sense of measure, so why it's of measure 0. Now, one may think we are shrinking these intervals, and since we have a series and each interval can be made arbitrarily small, but still to cover the union to cover A, one may think, well, because A is countable, it means it's small for having positive measure. Well, that's true. But now you may think, well, okay, if it's not countable, what if it's of continuum power? You might think, then it looks like it's the same cardinality. I mean, it is then of the same cardinality as a real line or as an interval. And you know that any interval, non-degenerate interval, is of some positive measure. Now, even though you have the two different intervals have the same cardinality, namely C, but different measure, you may think, well, okay, maybe cardinality does not is not so closely related to measure, so that cardinality almost means measure, and larger cardinality means larger measure, and vice versa. So obviously that's not the truth, but you might think maybe cardinality is related to whether measure of the set is positive or not. So you might think cardinality of countable must be 0, but maybe cardinality of uncountable set, let's say of a set of continuum C, must be some positive measure, because it looks like you have continuum many points, and you can somehow add them up, put them together in a line, I mean in a queue, and that queue will make interval, and that was a positive measure. You might think that's true. Well, is it? Well, let's see. Let's discuss Cantor set. So probably some of you have heard of Cantor set. So that's example. Next example. This was example with countable set. Now example with Cantor set. What's Cantor set? Okay. Cantor set is produced by creating a sequence of sets, decreasing in the sense of equation. So we are taking smaller and smaller sets, and eventually we are going to take intersection, and that's going to be Cantor set. So this is what I have in mind. Take interval from 0 to 1, okay? And I will denote that set. By C1, okay? Now next, in the next level, I'm going to take the previous one, but then I'm going to take out the middle third. So here is 0.1/3, and here is 0.2/3. And my C2, my set C2, is just this joint union of these two closed sets. I'm taking a closing. So when I said I'm taking out 1/3, I mean this middle third, but open interval from 1/3 to 2/3. Okay. In the next step, the third step, I'm going to repeat the procedure for each of subintervals in the previous step. So I take this subinterval and take out the middle third and again open interval. So what I'm left with is, instead of having this subinterval of size or length 1/3, I'm going to have two new subintervals, but now each is of length 1/9. So it's 1/3 of the length of the previous one. Okay, so I'm going to do that with the other one too. Okay, so we had these 4 points. They are going to stay in C3, but also we are going to take out middle third. So we now have 4 intervals. Now at level C4, at level 4, I'm going to have how many intervals? Well, each subinterval is torn apart and splits 1/3. The middle third is taken out, but the other 2/3 create are actually two new intervals. So at each level, to get the following level, you just create 2 times more intervals than you had in the previous step. Okay, so I have this set, this set, this set, this set, this, and now I'm taking out the middle thirds, so I'm having something like this. Okay, and now continue this procedure. So at each level, we are going to have how many sets? Well, here we have 1 set. Here we have 2 sets. So that's just 2. That's what? Okay, that's 2. Here we have 2 to the 2 squared. So that's 2 to the 3 minus 1. At this level, we have how many sets? 2 to the 4 minus 1. So at nth level, we have 2 to the n minus 1 sets. And what's the length of each subinterval, each of those sets? Well, the length is 1/3 to the n, obviously, right? So, or actually, well, the length of this guy is 1/3. The length of this guy is 1/3 squared. The length of this guy is 1/3 cubed. So actually, we have at level n, we have how many of these closed disjoint subintervals? Yes, closed disjoint subintervals. Let me call them I, K, N, and K goes from 1 to n. Right? So Cn is that disjoint union of these ikn's. K goes from 1 to n. So these are closed disjoint intervals, and measure or length of each of them is 1/3 to n minus 1, right? So 1/3, 1/3 squared, 1/3 cubed, yes, 1/3 to the n minus 1. And there are K doesn't go from 1 to n, it goes from 1 to, so how many of them? 2 to the n minus 1, right? Did we say that right? So when n is 2, we have 2 to the 2 minus 1. When you have n is 3, we have 4, so that's 2 to the 3 minus 1, yeah, that's 2 squared, 2 to the 4 minus 2 cubed, yeah, okay, so that's correct. All right, so what's the measure of Fn? What's the measure of Fn? Well, since it's this joint union of these, sorry, not Fn, Cn, okay? Measure of Cn. What's the measure of Cn? Well, it's the sum of the measures of all these. So each of them is 1 over 3 to the n minus 1. Since there are 2 to the n minus 1, many of them, so this is just 2 to the n minus 1 over 3 to the n minus 1. Okay, all right. So now the question, well, yeah, okay, so that's what we have. Now, as I said at the beginning, C is going to be the intersection of all these CNs, Cn, and goes from 1 to infinity. But Cn is decreasing sequence in the sense of inclusion. So we have that Cn contains the entire Cn plus 1. Okay? All right. So when you think of C, you can now wonder what's its measure. Well, since this is decreasing sequence and starting C1 has finite measure, and since C is the intersection of all of them, we can use a property that we discussed last time, continuity from above. So by continuity from above, we can calculate the measure of this set C. So that is going to be the limit of mu of Cn when n goes to infinity. But mu of Cn is this, so this is 2/3 raised to n minus 1, so that's obviously 0, okay? So the measure of this intersection of all these sets is 0. Now you can now say, well, this set C is what we call Cantor set. So this intersection is Cantor set. Okay, this is Cantor set. All right. Now its measure is 0, and one may think, well, okay, its measure is 0, maybe because it's too small, maybe because it's countable. And one argument for that, at least at first sight, would be that at each level n, you produce new endpoints of some subintervals, some disjoint subintervals I and k, and they remain in the entire sequence of CNs starting from that point. So it looks like every point of Cantor set is of that kind, and so it looks like you are producing finitely many, more and more finitely many points, and it looks like that is Cantor set, and looks like it should be countable. Well, actually, it's not quite rigorous proof, and it turns out that it's wrong. Here is the thing that I have in mind, why it's not countable. Well, it turns out, if you look at these endpoints of these closed intervals in the let's say let's first deal with left-hand points of these disjoint closed subintervals. So this point here is 2/3, okay? This point here is 8/9, but we can also write 8/9 as 2/3, so we jump 2/3 and then we add, so that's like we are jumping here 2/3, and then we add 2/3 squared, so 2/9, because each length here is 1/9, so we add from here, we add 2/9 to get here, okay? So this point, which is 8/9, can be written, we just showed geometrically that this point can be written, this left-hand point can be written as 2/3 plus 2/3 squared. Okay, you can check that this adds up really to 8/9. Now, what about this left-hand point here? Well, we are going at this level. We are going to pass jumping by 2, and at this level we are going to jump by 2 sizes of one of these. So 2 jumping from here to here, it's like adding 2/3 squared, because 1/3 squared is the size of each of these subintervals. So 2/3 squares, and then in this step we are going to jump one more by 2 of the sizes of each of the subintervals here. So this guy here is supposed to be what? 2/3 squared, 2/3 squared, plus, and then in this step 2/3 cubed. Okay, so that's this point here. This is 1/3. This right-hand point is 1/3, and this guy, since each length of each of these subintervals here is 1/3 cubed, so this is 1/3 minus 1/3 cubed. That should be the same as this. Okay, you just see that that's true geometrically. Okay, but if you see for any left-hand point of any of these subintervals, it looks like you can get to them by jumping by 2 measures of each of these subintervals I, k, n for some n. Okay, so adding up these, and that's really that's really true. Okay, about these left-hand points. Now, what about a right-hand point? Let's look at number 1. Number 1 can be obtained. Okay, you can get number 1 by jumping by 2 sizes at level 2, so that means 2/3 here, and then jump once again in the next level by 2 sizes of each of the subintervals here, so that means plus 2/3 squared, and then jump in the next level 2/3 cubed, and so on. So that's obviously the sequence of points that converges to this this number 1. In other words, we just see geometrically that if you take a series, if you keep jumping by 2 of the sizes of each of the subintervals here, so 2/3 to the n, you will get 1. Or actually, let me write here. You will get 1. Now, you can check that this geometric series really converges to 1. Namely, you can pull out 2/3 and get and have series n goes from 0 to infinity 1/3 to the n. The reason why I pulled out 1/3, not just 2, but also 1/3 as well, so in total 2/3. The reason why I pulled that out is because then I start counting from n equals 0, and I know the formula for geometric series when it starts from n equals 0. Now, it's just that I happen to memorize it in that way. If you memorize the formula for geometric series when n starts from 1, that's you can do in your way, but this is how I can compute. So we have 2/3 times, and if you start with n equals 0, series of q to the n, the series is equal to 1/1 minus q. So in our case, it's 1/1 minus 1/3. But this is 2/3, so you have 2/3 over 2/3, so that's really 1. That's correct. Okay, so we see that it really works. If you jump by 2 of the size of each subinterval here. Now, what about this right-hand point? This right-hand point here. Well, you can still jump by two sizes of some subintervals I, k, n. So to get this point, which is 1/3, you can jump at this level. So at this level, n equals 2, you just pass, you don't jump by 2. But at this level, you jump by 2, but now the size is 1/3 squared. So it's 2/9. Now you are here, and you want to get here. At this level, you jump once again 2 sizes, and so on. So we see actually, again, we have a sequence that converges to 1/3, and we actually get that 1/3 is the series. Now you don't start from n equals 1, you start jumping by 2 sizes from n equals 2. So this is series n goes from 2 to infinity, 2/3 to the n. Okay? And actually, in general, you see that, in fact, all these left hand and all these left hand and right hand points, or actually the entire Cantor set C, is actually the series n goes from 1 to infinity, an over 3 to the n, such that for every n, an is in 0, 2. Okay? Right-hand points are those so that starting from some n, all of them are 2. Left-hand points are those points so that starting from some n, an is 0. And there are also, so there are countably many of these points. But actually, one can see that when you take intersection of all these, every point in the Cantor set is of this form. So if you have a combination of zeros and 2, so zeros and 2s, so that there are infinitely many zeros and infinitely many 2s, those points are not neither left-hand point nor right-hand point, but are in the Cantor set C. Okay? So it's not, it's actually not that, Cantor set consists only of left-hand points and right-hand points of some of these intervals. So how can we see that actually not just the left-hand and right-hand points are actually points in the Cantor set, but there are all those. So left-hand points are points so that you have, now this is, you can notice this is just a ternary presentation of, there is a, well, okay, forget about it for the moment. So we can write, well, okay, you can think of this series as a ternary presentation of some number. So we can write in the ternary presentation of this number is just point, and now you have some zeros and 2s, so depending what the ANs are. But now we saw that left-hand points are of the form some combination A1, A2, so these are now, ANs are either 0 or 2, A1, A2, blah, 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 some AN here. And for left-hand points, the rest are 0. So starting from some n or n plus 1, the rest are zeros. So these are left endpoints, and right endpoints are of the form some a1, a2, blah blah blah, an, and then 2, 2, 2, 2, 2, 2, and so on. So this number here is just the left endpoint, and if these a's are the same as these a's, so these two guys are left end and right end point of the same subinterval at level n or n plus 1 or n minus 1. Let me just think. So what did we say at level 3? This is left hand point up to this guy. So that's at level 3. Okay, so this is actually at level n plus 1. So for some k in between 1 and 2 to the n, because we said there are 2 to the n minus 1 subintervals at level n, but this is for level n plus 1. So for some k in between 1 and 2 to the n, these two guys are left end and right end point of a k n plus 1. Okay? Alright, but now inside that interval, you now continue doing that process of taking out middle third and just keeping the other 2/3. And by doing that, what you are doing actually is that now in the next step, you are adding here some 2's, all right? So you are basically now taking out points so that you are still in this interval in between these two numbers, but endpoints of these new intervals will be some numbers in between these two. So that means some numbers, so that starting from this point, all will be 0, and starting from this point, all will be 2. Okay? But all the numbers in between are included. So basically, you are including in this next step, you still keep numbers which have infinitely many zeros and infinitely many 2's, because there are infinitely many numbers, or continue many numbers, of course, in between these two, and that's just simply because there continue many ways to have some combination of zeros and 2's, so that number is still in between these two numbers. Okay, so basically it's not that you are just having left end and right end points or some Cn or some subintervals ikn. The Cantor set C contains all the points of the form 0, 2, 0, 2 with infinitely many zeros and infinitely many 2's. Okay, so because of that, C is exactly equal to this. But not only that, since you can think of since these are just ternary representations of left hand and right hand points of Cn, or actually of Cn plus 1, so some interval ikn plus 1, we have that the cardinality of C is equal to the cardinality of the collection of all sequences of zeros and 2's. All right, but that's a continuum, because collection of all zeros and 2's is just a collection of all such sequences is just like collection of all sequences of zeros and ones. Now when I'm taking zeros and ones, because now every number can be written in binary form. So every number, every real number, if you take its binary representation, so it's going to be on the form bn over 2 to the n, every number between 0 and 1, and goes from what, from 1 to infinity, where bn's are now all the digits that you use in the binary system. So obviously there is a bijection between these two. Simply anytime you have a sequence of zeros and twos, convert twos into ones, and obviously that's a bijection. So Cantor set has as many points as these sequences of zeros and twos, and that collection is this, of the same cardinality as collection of all sequences of zeros and ones. But sequences of zeros and ones are nothing but the binary presentations of real numbers. So basically, there are as many points in Cantor set as real numbers, and that shows that actually Cantor set is of continuum power. Okay, so here we have set which is of continuum cardinality, but we've shown that it's of measure 0. Okay, so that clarifies some things about relation between measure and size in the sense of cardinality of the set. So it's not that if you are countable you are measure 0, that's fine, but it's not that that means actually that cardinality always affects the measure, the size in terms of measure of the set. So we just seen that there are examples of, there is example of set which is of continuum power, but still of measure 0. Okay? All right. What's next? So now we see that we have a problem. If you, how many subsets of C? So P of C is a power set of Cantor set, and the cardinality of power set of any set is strictly greater than the cardinality of that set. So we have this, that's actually for every set, so C, so in particular for C being Cantor set. But this is of continuum power, okay, and the same continuum power, of the same continuum power is Borel sigma field on R, okay? So we see that the cardinality of Borel sigma field is strictly smaller than the cardinality of all subsets of C, of Cantor set C. Now, that's something that produces an inconvenience to us. Namely, if mu of C is 0, we would like any subset A of R to be measurable so that we can assign measure, and moreover that measure is 0. So, sorry, if A is a subset of C, I should say subset of C, we would like mu of A to be less than or equal to mu of C. I mean, if A is measurable and A is subset of C, then this is definitely true. But since this is 0, mu of A should be at measure 0. However, our problem is that C has uncountably many subsets, because C is countable, so its power set is uncountable. Sorry, not uncountable, uncountable, but actually has a power or has cardinality greater than C. So if you take arbitrary subset of C, you would like its measure to be, you would like that we can assign a measure to it, and moreover, its measure should be 0. But now problem is that there are more than continuum many such sets A, because this is strictly greater than C, but B of R only has continuum many sets. So that means there are a lot of sets which are subset of C which are not in Borel sigma field. So that's the problem. So it looks like, in some sense, the Borel measure mu is not complete. Not complete in the sense that if some set is measurable, so in the sigma field, and is of measure 0, it's not true that all of its subsets are of measure 0, because simply some of each subsets are not in that sigma field, so you cannot assign a measure, because that measure is defined only on that sigma field. Okay? So for that reason, we would like to extend definition of measure from Borel sigma field to some larger, some broader sigma field, which of course agrees on Borel sigma field with Borel measure. In other words, that larger measure, I mean that measure defined on a larger sigma field, its restriction on Borel sigma field is the same as what we have so far, the same measure as this Borel measure. Okay? But it simply just involves those subsets of sets of Borel measure, and we would like to include all those subsets of some Borel set of measure 0. Okay, and that can be done, that extension can be done. Let me see how much time I have. That can be done, and that extension is called Lebesgue measure. Now, there are several ways to extend Borel sigma measure, sigma field to Lebesgue sigma field and Lebesgue measure. So one way is just to follow the idea of the proof that the second proof that the countable set is of a finite Borel measure. Is of 0 Borel measure. So you have a covering and sequence of coverings, and covering is by intervals, and the total sum of lengths of intervals, that sequence converges to 0, and that shows that the set that showed in our proof that the countable set that we dealt with had measure Borel measure 0. Now the same idea can be applied for every set. Okay, actually for every subset of omega. So where omega is arbitrary set, we can define measure. We can define a set function, not a measure. Set function on P of omega in the following way. Well, actually, I'm just going to take omega to be real set of reals, but omega can be r to the d for any dimension d. So let A be a subset of R. I'm going to define a set function, which I will call mu star or mu superstar, that is defined, so its domain is the entire power set of reals, and it's non-negative, okay? And we're going to define it in this way. Mu superstar of A is, now take any finite or countable covering of, well, actually take elementary sets. So remember, collection of elementary sets are disjoint, finite disjoint unions of intervals. So take finitely many or countably many, so that means at most countably many ENs, and if that's the covering of A, so if A is subset of a union of ENs, then take the series or finite sum of all those mu of En, where mu is Borel is a Borel measure. So mu is defined on finite disjoint unions of intervals. Okay, so we can discuss all of these, and because of this property, we expect that, we would like the measure of A to be less than or equal to this one, okay? But the measure, we did not define measure for any subset of P of R. So what can we do? How can we define this mu star of A? Well, we can define it just as an infimum, so the largest lower bound, infimum, over all these guys, u of En, where this sequence, when this sequence En goes over all finite or countable collection of all finite or countable collection of elementary sets. So we can say that this sequence is in e to the less than or equal to n. That's in some books, and some professors use this notation. So that means En, this sequence En, is finite or countable sequence of elementary sets. That's all what this means, all right? So that means, such that, okay? So this is a number, so this is Borel measure. So mu of En is just the sum of, so for each En, since En is a finite disjoint union of intervals, mu of En is just the sum of those lengths of those intervals. And so, so that's for each En. Now, if you have at most countable covering of set A, you take this sum, which can be finite or infinite, in which case it's series. So basically, this is the idea. You have A, all right? This set A, and now this is now in 2D. We define here for on the real line, but the same thing is when you have r squared or r cubed or blah blah blah, r to the d. But maybe it's it's easier to grasp the idea if you just consider d equals 2, what we are doing when d equals 2. So we have, this is 1 e. So this is one elementary set. This is now another elementary set. So those red rectangles are disjoint, black rectangles are disjoint. Now this is another elementary set. So let me say this, and let me say this, okay? And then we have another, the blue one, say this set, and let's say this one. Well, okay, let me have one more black in the first. Okay. So black rectangles, their union is E1. Red rectangles, their union is E2, set E2. Green rectangles, their union is E3, and blue rectangles, their union is E4. Okay, definitely these four elementary sets cover the entire set A. Okay, and compute the total measure of all these. Okay, the sum, actually compute this sum. It's obviously it's going. There will be a lot of overlapping, but we can do a bit better approximation. Namely, if you take smaller subsets, okay, smaller and smaller, and we are even allowed to take countably many of ENs. So the smaller sets, even if, the smaller sets are these ENs, the more accurate, the smaller this is going to be, as long as this is a covering, and the more accurate the sum or the series is. By more accurate, I mean the closer this series is to what we would like to be the measure of this black set. So of this set, okay? So when you take infimum over all those coverings, so that's where you are going to, that's how you are going to define mu star. Now, to define measure on the entire real line, we can first focus on just just interval 0, 1, and if A is a subset of this interval, we are going to define mu superstar of A in this form, where ENs are now elementary set, not arbitrary elementary set in R, but elementary sets which are inside this unit interval 0, 1. Okay, and then we can also define mu substar of A simply to be 1 minus mu superstar of A. Now we can show, this is just a brief sketch of construction of Lebesgue measure, so I'm not going to prove these things, but one can show that, so here is a claim, that mu substar of A is less than or equal to mu superstar of A for every A subset of 0, 1. Okay, the reason why we have 1 is, well, you can think of some kind of complementation here, but I don't have time to discuss that in detail. So for every set A, you have this. Now note that mu star, mu superstar, is defined for any subset, and that's ideal that measure is defined for every subset. But we saw actually that's if you want measure to be defined as a set function which is countably additive, it will, and that measure of each interval is equal to each size, or proportional to its size. I mean b minus a, right hand point minus left hand point. That implies that measure is translatory invariant, and in Vitali set we used that property, translation invariance. So you cannot actually have a countably additive set function, non-negative set function, for defined on the entire collection of all subsets of R, so entire P of R. So what's the problem? Well, mu star is finitely additive, that is true, but the problem is mu superstar is not countably additive. However, it is countably sub-additive in the sense that if this is true, then mu superstar of A is less than or equal to, now these mu's are the same as mu superstar, because mu superstar obviously agrees with mu, with Borel measure on Borel, actually intervals, okay? So this is so-called, this implies this is so-called sigma subadditivity or countable subadditivity, but we don't have that if this is disjoint union, when A is equal to disjoint union of ENs or some intervals, some sets, then the mu star is equal to the series of mu star of each term. So each component. So that's the problem with mu superstar. You cannot have countably additive or sigma additive set function on the entire non-negative set function on the entire power set of R. So we have to restrict ourselves to some narrower collection of sets, and that narrower collection of sets is going to be the collection of all subsets of R for which mu substar of A is equal to mu superstar of A. So that's, so let me write here. Let L be a collection of all subsets of, now we actually have P of 0, 1. We just restrict it to P to 0, 1. So L is, well, let me say L1. Collection of all A subsets of this such that mu substar of A, which is defined for every set A, is less than or equal to mu superstar of A, which is also defined for every A. So why is mu superstar defined for every A? Because this is a collection of, these are just non-negative real numbers. And so this set is definitely bounded by 0 from below and by one of the famous theorems or axioms of real numbers, depends what you choose as a collection of axioms of real numbers. You have that infimum of this set exists. So that's why mu superstar of A is defined for every A. Okay? But the problem is it's not sigma additive. It's just it's just finitely additive, but not sigma or countably additive. Okay, so this is now this is so-called Lebesgue. It turns out that this L1 is Lebesgue sigma field on 0, 1. Now, how are you going to define? This turns out that this is a sigma field on 0, 1. Now we call it Lebesgue sigma field. Now, how can you extend the definition of this for every subset of R, or instead of 0, 1, now you can consider n plus 1 for any integer n, and just shift everything. So if A subset of 0, 1 you define in this way, so if A subset in n plus 1, you define mu star of each of these, mu star of A in this way, but now ENs are going to be from this interval, okay? And finally, if you have a set which is a little bit in 0, 1, a little bit in -1, 0, a little bit in 1, 2 interval, so you can define, you can say that it can be partitioned. So this is actually the disjoint union of A intersected with n plus 1, and n goes from 1 to infinity. That's obviously true. And now for each part here, you have defined mu superstar, okay? And if this guy, oops, sorry, I made a mistake here. This should not be less than or equal to, but equal to. Okay, so I'm sorry. So in fact, the Lebesgue sigma field is the collection of all sets A for which this is true. We know that for every A, mu substar is less than or equal to mu superstar, but we actually have, when they are equal, we say that A is Lebesgue measurable on 0, 1, and the collection of all Lebesgue measurable sets is, I just denoted by L1, and it turns out that it's a sigma field on 0, 1. Now you just extend for every A subset of real numbers, you just partition it into pieces in each of these intervals of unit length, and if each piece is Lebesgue measurable, so you define a Lebesgue measure on each of these pieces in the same way. It's just that ENs are in these E's are in this set. So you can talk about Lebesgue measurability of this set, and now if each of these pieces is Lebesgue measurable, then we will say that A is Lebesgue measurable, and that its measure is the sum of measures, mu star measures of these guys, okay? So Lebesgue measure A, that's what Lebesgue measure A is, and that's a standard measure used in probability, okay? And with respect to which we, for example, compute probabilities when we deal with the uniform distribution. So any uniform probability of uniformly distributed random variable to fall into some set is proportional to the Lebesgue measure of that set. Okay. It is easy to see that this Lebesgue measure is just extension of Borel measure, in the sense that any Borel sigma field, any Borel set is also Lebesgue set, Lebesgue measurable, and that Lebesgue measure, so that's this mu star, for which mu star is equal to mu substar. Every Borel sigma field, every Borel set satisfies this. Okay, so that's the extension of Borel sigma field to Lebesgue sigma field, and extension of Borel measure to Lebesgue. And before we finish the class, I would just like to say that Borel, that the Lebesgue measure is complete in the sense that, so let's go back actually to Cantor set. We saw that Cantor set is the intersection of those CNs, right? But now Cn is Borel set. Actually, it's an elementary set because the Cn is the union, disjoint union of some closed intervals. Okay, so Cn's are elementary sets, so they are Borel sets, and so countable intersection is also Borel set because Borel sigma field is a sigma field, so it's closed under countable intersection. So C is Borel sigma field, and as I said, the Lebesgue measure is extension of Borel measure, so let me call lambda measure defined on L. L is all Lebesgue measurable sets, so that means all sets for which mu superstar of A is equal to mu substar of A. After you actually, so after you partition A into pieces that are in intervals n plus 1, so each piece, let me call an piece that is in n plus 1 interval, each piece satisfies this, so then the measure that set A, which is the disjoint union of these ANs, is actually Lebesgue measurable, so that's what it means, collection of all Lebesgue measurable sets. So it maps L to 0, 1, 0, infinity. So it turns out that, as I said, Borel sigma field is contained in L, and that for any B in B of R, Lebesgue measure, so lambda stands for Lebesgue measure of B is actually mu of B, where mu is Borel measure. MSRE. This is this is standard abbreviation for measure. To write measure. Okay, Borel measure. All right. So, so in particular, since we showed that mu of C is 0, and C is Borel set, so lambda of C is also 0 because these two are equal. Now, why do we? Okay, so that's what we have. But what? But what I wanted to say now, it turns out that a lambda, the Lebesgue measure, is complete in the sense that actually for every subset A of the Cantor set, we have that A is in L. In other words, that lambda of A is defined. And since A is subset of C and lambda is measure, and the lambda of C is 0, we definitely have this. So in other words, lambda of A is 0. Okay? We could not say that mu of A is 0 for every subset of C, because not all A's subsets of C are in Borel sigma field BOR. Okay, so lambda is complete, and this is completely satisfactory for us, and we are going to work with Lebesgue measure, but you can always think of Lebesgue measure as the extension of Borel sigma field, Borel measure, and Borel measure is just a generalization of, it's like a generalized length of interval. So we generalize it to the length of some subsets, not all subsets of R. And similarly in R to the D. Okay. That will be all for this time.